Multilayer Perceptrons. The perceptron is the basic processing unit. It has inputs that may come from the environment or may be the outputs of the other perceptrons. Associated with each input xj, which is in R, and j is the index starting from 1 to d, is a connection weight or synaptic weight wj in R, and the output y in the simplest case is a weighted sum of the inputs. See figure 11.1, that y equals to the sigma summing for all j starting from 1 to d of the term wj times xj plus w0. W0 is the intercept value. To make the model more general, it is generally modeled as the weight coming from an extra bias unit x0, which is always plus 1. We can write the output of the perceptron as a dot product y equals to w transpose times x, where w is equals to the transpose of the vector w0, w1, w2, and so on until wd, and x is the transpose of 1, x1, x2, and so on until xd, are augmented vectors to include also the bias weight and input. During testing, with the given weights w for input x, we compute the output y. To implement a given task, we need to learn the weights w, the parameters of the system, such that correct outputs are generated given the inputs. When d equals to 1 and x is fed from the environment through an input unit, we have y equals to wx plus w0, which is the equation of a line with w as the slope and w0 as the intercept. Thus, this perceptron with one input and one output can be used to implement a linear fit. With more than one input, the line becomes a hyperplane, and the perceptron with more than one input can be used to implement a multivariate linear fit. Given a sample, the parameters wj can be found by regression. See section 5.8. The perceptron, as defined in equation 11.1, defines a hyperplane, and as such can be used to divide the input space into two: the half space where it is positive and the half space where it is negative. See chapter 10. By using it to implement a linear discriminant function, the perceptron can separate two classes by checking the sign of the output. If we define s dot as the threshold function, s of a equals to 1 if a is greater than 0, s of a equals to 0 otherwise, then we can choose c1 if s of w transpose times x is greater than 0, and we can choose c2 otherwise. Remember that using a linear discriminant assumes that classes are linearly separable. That is to say, it is assumed that a hyperplane w transpose times x is equals to 0 can be found that separates x to the t, which is in C1, and x to the t, which is equals in C2. If a later stage we need the posterior probability, for example, to calculate the risk, we need to use the sigmoid function at the output as O equals to W transpose times X, and also Y equals to sigmoid of 0, sigmoid of O, that O that we just defined, W transpose times X, which is equals to 1 divided by 1 plus exponentials of minus W transpose times X. Figure 11.2 is the representation of k-parallel perceptrons. X, j starting from 0 to d are the inputs, and the yi starting from 1 to k are the outputs. Wij is the weight of the connection from input wxj to output yi. Each output is a weighted sum of the inputs. When used for k-class classification problem, there is a post-processing to choose the maxima, or softmax if we need the posterior probabilities. When there are k greater than 2 outputs, there are k perceptrons, each of which has a weight vector wi. See figure 11.2. That is yi equals to the sigma summing for all index j starting from 1 to d of wij times xj plus wi0, which is equal to wi transpose times x, and y is equal to w, capital W, times x. If we just use the symbol for simplification, where wij is the weight from input xj to output yi, and w is the k by d plus 1 weight matrix of wij whose rows are the weight vectors of the k perceptrons. When used for classification during testing, we choose Ci if yi is equals to the maxima yk, where the maxima is taken among all possible k, and in the case of a neural network, the value of each perceptron is a local function of its inputs and its synaptic weights. However, in classification, if we need the posterior probabilities instead of just the code of the winner class and use the softmax, we also need the values of the other outputs. So, to implement this as a neural network, we can see this as a two-stage process, where the first stage calculates the weighted sums, and the second stage calculates the softmax values. But we still denote this as a single layer of output units, that is OI equals to WI transpose times X, and YI equals to exponential of this OI divided by the summations of exponential of OK and summing for all k. Remember that by defining auxiliary inputs, the linear model can also be used for polynomial approximation. For example, define x3 equals to x1 to the square, x4 equals to x2 to the square, x5 equals to x1, x2, section 10.2. The same can also be used with the perceptrons. Durbin and Rumihart in 1989. In section 11.5, we see multilayer perceptrons where such nonlinear functions are learned from data in a hidden layer instead of being assumed a priori. Any of the methods discussed in Chapter 10 on linear discrimination can be used to calculate the wi, I starting from 1 to k offline and then plugged into the network. These include a parametric approach with a common covariance matrix, logistic discrimination, discrimination by regression, and support vector machines. In some cases, we do not have the whole sample at hand when training starts, and we need to iteratively update parameters as new examples arrive. We discuss this case of online learning in section 11.3. Equation 11.5 defines a linear transformation from a d-dimensional space to a k-dimensional space, and it can also be used for dimensionality reduction. If k is less than d, one can use any of the methods of Chapter 6 to calculate w, capital W offline, and then use the perceptrons to implement the transformation. For example, PCA. In such a case, we have a two-layer network where the first layer of perceptrons implements the linear transformation and the second layer implements the linear regression or classification in the new space. We note that because both are linear transformations, they can be combined and written down as a single layer. We will see the more interesting case where the first layer implements nonlinear dimensionality reduction in section 11.5.